Hello, and thank you for joining us for today's webinar, The Value of FDM End-Use Parts. Who, what, where, when, and why. My name is Kim Kaloran, and I'll be your host for today's event. Before we get into the topic, I wanted to give you a brief overview of Stratasys. For those of you who aren't familiar already with our company, Stratasys manufactures 3D printing equipment and materials that create physical objects directly from digital data. Its systems range from affordable desktop 3D printers to larger, more advanced 3D production systems. We are passionate believers in the value and power of 3D printing and the change it can bring to the world. All Stratasys 3D printers build parts layer by layer. PolyJet technology employs an inkjet-style method to build parts from liquid photopolymers in fine droplets that immediately then are cured with a UV light. FDM technology, fused deposition modeling, extrudes fine lines of molten thermoplastic, which then solidify as they're deposited. The Stratasys portfolio of 3D printing materials is the most comprehensive in the industry. It includes over 500 PolyJet photopolymers and FDM thermoplastics. So now on to today's event. One other actual quick note before I introduce our speaker. At the end of this webinar, you will get a link where you can access these slides along with the recording of the webinar and other information on the end-use parts application. So now, I'd like to welcome our main presenter today, Jeremy Hoyt. Jeremy is a member of the corporate FDM applications team here at Stratasys. He holds a master's degree in materials science and engineering from the University of Minnesota. So Jeremy, take it away.
Thanks, Kim. Appreciate the introduction there. Before we begin talking about the value of FDM for end-use parts, I want to take a step back and take a look at the applications within the additive manufacturing space. The two main categories being design and manufacturing. So concept models and functional prototypes are on the design branch, and concept models are primarily used to validate fit and form, while functional prototypes take it a step further and are used for testing prior to full production. On the manufacturing side, there are manufacturing tools and end-use parts. Manufacturing tools such as jigs and fixtures are discussed in another webinar, which is available on stratasys.com, and of course today's topic is end-use parts. So FDM end-use parts is quite a broad topic, so I'll be speaking in some general terms today. But one of the main points I want to make is that using a system to produce end-use parts leverages the full system capability and provides the highest ROI and best ROI because of the high system utilization rate. So when a user uses their system to produce end-use parts, they're getting a greater utilization rate, much greater than design-only users. And as a result, they're realizing significant value as a result of some of the technical benefits as well as some of the process improvements, which translates to savings in cost as well as time. Of course, the greatest savings are being realized in regions with the highest labor costs. But the good news is that nearly anyone can reap the benefits because, as I mentioned, it's a broad topic, and that's primarily because it's applicable to virtually any industry. Here's a brief video that I think highlights some of the benefits of FDM.
Efficiency plummets and costs escalate with small batch on-demand production of finished goods. This is true of injection molding, die casting, CNC machining, and most other production manufacturing processes, but not with FDM. For end-use parts and production-grade thermoplastics, FDM is a better alternative. Make optimized, highly complex finished goods for all your low-volume manufacturing orders.
We use this technology for production parts.
You're never stuck with one design.
It really has changed the whole industry significantly as far as how long it takes to get products to market.
Shift from product design to production in a single day and eliminate the expense of tooling, setups, and changeovers to save up to 90%. Shift your production work to FDM. Visit stratasys.com to find your local reseller and discover all the advantages.
So even in that brief clip, we see a wide variety of ways that FDM delivers value through its unique benefits. And I think we're going to go ahead and explore that today, and we'll do that by taking a look at the who, what, where, when, and why of end-use parts. So we'll begin with a brief application overview. We'll continue on to discuss where FDM end-use parts are used. Then we'll dive into some of the traditional processes that FDM can either complement or replace. Then we'll look at FDM's role in producing end-use parts and when FDM fits best. We'll highlight many of the benefits of FDM for end-use parts, and then we'll take a good look at a customer success story with some pretty vivid details. So let's begin by defining the application of end-use parts as the use of FDM for production of finished goods or sub-assemblies. Typically, when we're talking about using FDM for end-use parts, we're talking about replacing plastic parts. In some instances, though, we can replace either metal or parts made of other materials as well. So FDM is an option at any point during the production cycle. That includes pilot production, where you're doing production simulations even before you have your production line set up. It also includes bridge to production when you want to be making parts while you're waiting on your tooling and waiting for your production line to be set up. It's also an option for full-scale production, so you can completely replace your traditional method to use FDM to manufacture those end-use parts. And during the end-of-life production cycle, where you can use FDM to extend your product life and product support without having to replace aging and failing tooling. So you can produce spares or extra parts for use as repair parts, even after your pre-existing or traditional production method has been retired. So there is a broad catalog of durable goods where FDM is used. There really is no link to the company size, the product type, or any target market. FDM production of end-use parts can be a benefit wherever plastic parts are manufactured. So having said that, I guess it wouldn't be surprising for me to say that FDM end-use parts are widely adopted and they can be found in most major industries. The bottom corner of the slide here is just a brief list of some of the industries that have adopted and are currently using FDM to produce their end-use parts. So it ranges from aerospace companies and automotive all the way to medical devices. Who can benefit from FDM? Primarily, it's manufacturers using plastic components for finished goods. And beyond that, it's manufacturers that are looking for a cost-effective, low-volume production method. It's also manufacturers that are looking to get around some limitations due to either time constraints or cost constraints or constraints on their design freedom because of their traditional method. It's also manufacturers that are needing to add needed flexibility and efficiency to their production method. One thing that all manufacturers that are adopting FDM for end-use parts have in common is that they're open to change and they're seeking to innovate. So on this slide, you see just a cross-section of the variety of companies utilizing FDM for end-use parts. You can see from this slide that it ranges from smaller companies like Assist Medical all the way up to larger organizations such as NASA. It also spans the entire range of industries from, say, a custom motorcycle shop such as the Orange County Choppers to medical and aviation equipment. So now we've got an idea of the who, what, and where. Let's begin our discussion of the why. And we'll start that by examining some of the traditional processes. For injection molding, it requires machined tooling, injection molding equipment, and plastic molding. So for every design iteration, you need a new plastic mold, which can be limiting in an operation. There's also the option of machining, which requires fixture setup and time to cut parts, and any changes to designs or adding complexity often adds to cost and time. With RTV molding, room temperature vulcanization, or reaction injection molding, these can be great ways to make very high quality urethane parts, but they're all dependent upon making a good pattern or a good mold, which depends on, again, machining, either manual or CNC machining. For all these traditional processes, anytime you're adding features, complexity, or changing your design, you're adding or increasing to cost and time. Additionally, all of these processes require skilled labor to monitor or run the process. This brings us to FDM's role, which is an alternative completely or as a complement to traditional methods. It's a capable way of producing parts during any part of the production cycle, and it's great for customer configured products with the added benefit that no tooling is required. So there's no lag process as you're sending out your design to be machined to make a mold or tooling. Additionally, it's an automated process, so you can take advantage of some cost savings there, as it doesn't require monitoring 24/7 or forever period whatever your operation is operating. Because of these improvements in these process conditions, you can go from the prototype stage or design stage all the way to production in a single day. So when is FDM a best fit? FDM is a best fit when we're talking about part volumes and quantities of 1 to the low 1,000s, when the size of the part is less than or equal to 300 millimeters per side. Now, that's a best fit and not a hard and fast rule, as we have customers that are using FDM to produce end-use parts that are larger than that. Because we're talking about end-use parts, we do have to take into account the operating conditions or other conditions that the part might see. So the material properties of our thermoplastic materials have to be in line with what those parts will see. We're talking about the mechanical properties, electrical properties, any chemical resistance properties, as well as thermal properties. FDM has an accuracy of around 0.13 of a millimeter. For parts with tighter tolerances than this, secondary processes can be used to ensure confirmation to those more stringent requirements. FDM is also a best fit when we're talking about custom or configured to order parts, such as you see on the right-hand side of the screen. It's also great for items that might see frequent stock revisions or frequent redesigns. Finally, situations where designs are complex or design for performance requires an iterative process is a great fit for FDM as well. So what are the benefits of FDM? The primary benefits of FDM are savings in lead time and cost. With FDM, as soon as your design is finalized, you can go to production immediately. There's no lag there for making machining tooling or molds. You can immediately begin production, which results in a 75 to 90% reduction in that time to market. On the cost side, there's no upfront costs, no expenses sending out designs to be machined either by hand or by CNC. And we're also saving costs by reducing the labor costs because of the automated nature of FDM, resulting in a 50 to 90% reduction in costs. FDM truly is a just-in-time manufacturing method, so you can manufacture the parts as needed and when needed. You can eliminate carrying costs by transitioning to a digital inventory. And say, for example, if you have multiple locations, you can share that file digitally, and you can make the part when and where it's needed. Additional benefits of FDM are design freedom. So designers and engineers will gain design freedom. With FDM, they're not constrained by manufacturability rules, such as with injection molding. They can also design for optimized performance, not for the manufacturing method. They can also consolidate part count, reducing a multi-part design to either a consolidated part design or a single part design. And they gain flexibility in multiple ways. You can gain flexibility to incorporate even minor changes because it doesn't require sending out for machining or mold making. You can do it in the file and then queue that for the print job. Additionally, you can switch up your product mix simply by reorganizing the queue. Or there's the additional option to print multiple parts side by side at the same time. Finally, FDM is an automated process and can be a true lights-out operation. It provides the freedom to prepare a job for printing and have the machines run either overnight or over the weekend, so you can go home and come back and take the parts off in the morning. So now we've covered the who, what, where, when, and why. Let's look at a customer success story. NOVATECH Engineering is a Stratasys customer that manufactures automated equipment for fowl hatcheries. They really leverage the benefits of FDM, and they use their parts, or the parts manufactured by NOVATECH, are used to ensure safety of fowl during inoculation, which aids in their livestock management. So as I said, NOVATECH produces these parts for livestock management. You see the part there on the right. They were previously using an injection molding process to make it. One issue with that is that for each system that they design in each species and breed, it required a different mold design. It was quickly limiting their growth, and so they were looking for an alternative way. They already had a Stratasys dimension machine in-house for prototyping, but decided to try FDM for their pilot production. So they began by producing parts in PCABS and eventually added and incorporated design for FDM principles so they could get rid of features that weren't needed and they could go ahead and take advantage of FDM features like sparse fill and self-supporting angles to reduce their materials costs and speed up their build times. For the one part you see alone there, taking that to pilot production, they saved $42,000 just because they weren't sending out to make tooling for it. You can see here that cost savings is a 97% cost savings, and on the time side, they were able to cut their time down from weeks to simply days. This was for a single part design. When they multiplied that by the number of part designs that they needed to do, it quickly justified for them purchasing additional Stratasys systems. They also had advantages from the ability to add design changes on the fly and switch that digital inventory. But of course, NOVATECH is just one of many companies that found that transitioning to FDM was the right choice. Literally a world away, NASA is finding ways to put FDM to use on their space exploration vehicle. And here's that story.
We retired the space shuttle this past year after 30 years of excellent service to our nation. And its time had come. It had been a fantastic program. It had done amazing things. But now NASA is ready to really take the next step, which is a more continued presence in outer space beyond low Earth orbit. Our ultimate goal is to get humans to Mars. When we started this project, we thought we were really clever thinkers. We had some technology we wanted to explore that involved multiple wheels and the ability to turn in any direction. They thought, well, what if we build a cabin and have the crew go out for multiple days? And that's really where this small pressurized rover concept has really evolved into a space exploration vehicle.
So the SUV will hold 2 astronauts. They basically live in this module, in this rover. It's your own personal SUV in space. You always want it to be as light as possible. You also want it to be strong enough that it's got your safety factors, that nobody's going to get hurt. You're going at several thousand miles per hour just to escape the Earth's atmosphere. So you've got to be able to handle all these vibrations and all these different things just to be able to get out into space. And the vehicle can't be damaged. There's probably around 60 to 80 parts on this particular rover. It's all done by additive manufacturing for a lot of different reasons. You know, sometimes traditional manufacturing methods don't really work for some parts that you want to build, where you can do it with additive manufacturing, and it's really simple. It really takes no effort for what would otherwise be a very complex process. Whether it be ducting that's got flame retardant characteristics and properties to it to help keep people safe, or different fixtures and different parts. There's absolutely a place for additive manufacturing. There's a lot of things that you don't see that really get to go on is the design verification and the functionality checks of parts before we send them to be manufactured. If the final product is not going to be an additive manufacturing plastic part, we will do it in a rapid prototype fashion where you'll get it back in maybe an hour, a day. What that allows us to do is be able to check our design and make sure that everything's going to work the way we think it is. Sometimes vendor components are a little bit different than what you anticipated, what the drawings say. So you're able to functionally build up this assembly and check it to say, hey, this is what we want, or hey, we need to make some tweaks. So by doing additive manufacturing and rapid prototyping, it allows you to keep your costs down. Everybody's got a budget to deal with, and we're no different. Being able to make a difference and leave my mark is really what inspires me. You know, that's what gives me the drive to do what I do.
So that is a look at how NASA uses FDM on their space exploration vehicle. But as I said at the onset, and I think I've reiterated throughout this presentation, FDM for end-use parts is applicable to all industries. I think that better than putting up another list of a wide range of industries, I want to show you the following clip to illustrate that point.
An end-use part is any tangible good that is sold as product, used as a subassembly, or as a component in a product, but they may not be sold at all. End-use parts are also placed in service within the company's own operations. For example, a component used on its packaging equipment. Almost all industries, from consumer electronics to aerospace and military, utilize end-use parts, and they come in all shapes, sizes, and materials, from plastics to metals. For those plastic parts, FDM is an alternative for pilot runs to full-scale end-use part production. FDM offers a more flexible and inventory-friendly manufacturing solution that is fast, cost-effective, and efficient. Traditionally, parts are manufactured using processes such as molding, casting, and machining. For each of these processes, the primary focus is on how to design for capability, optimization, and efficiency. Because of this, once the process has been developed, it is static, and with any change, cost rises, throughput drops, and manufacturing efficiency tumbles. With FDM, this is not the case. FDM allows for optimization of part design for function and a dynamic production environment that not only allows but encourages continuous improvements and design modifications. This flexibility enables companies to expand their product lines and markets served with solution-based selling. Affordable and efficient low-volume manufacturing becomes practical. FDM is a best fit when production volumes are anywhere from a quantity of 1 to 1,000, and the designs are moderately to very complex. An order quantity of 1 usually means customized products. Industries such as medical or motorsports are two examples where customized products are commonplace. In the medical field, FDM is used for things like prosthetics and surgical guides. In motorsports, manifolds, instrument pods, and hood vents often rely on FDM. Aerospace is an example of low-volume, high-value production, which is ideal for FDM. FDM is used for end-use parts throughout the entire product life cycle. During the alpha and beta phases of product release, it can be used to make parts for pilot production runs. Some will use a raw FDM part. Others will use secondary operations such as sanding, filing, or automated processes to get production-ready parts. Once the product has been validated and all component designs are frozen, FDM can be used as a bridge to production, making end-use parts while waiting for delivery of tooling and manufacturing equipment. For some of the more complicated geometries and customizable solutions, full production with FDM is the practical option. Since traditional tooling is aimed at production of a single design, FDM is an efficient and optimized solution for products that are continuously changing, either through product revisions or through order-by-order customization for products such as prosthetics. When a product approaches the end of its life, companies once again turn to FDM. As orders decline and tooling requires replacement, FDM is an alternative that extends the product's life with minimal expense and little or no inventory to carry. In this phase, or after a product has been retired, FDM can also continue to manufacture spare parts as they are requested. So what qualifies a part as a good candidate for FDM end use? 1. The design is expected to change frequently. 2. The part is a one-off. Look for the customized product or the solutions-based products that are encountered in motorsports and processing equipment, for example. 3. Production costs can be decreased by consolidating parts so that there are less components to assemble and manufacture. 4. The product demands or deserves a design that is impossible or impractical to manufacture with traditional methods. Companies that are open to change and innovation, open to non-traditional manufacturing approaches, are also open to making adjustments to the traditional design process to fully capitalize on all the benefits FDM has to offer. For further information, contact Stratasys Application Support.
So to summarize what we've discussed here today, we've discussed what end-use parts are, that FDM is applicable during any stage of the production cycle. We've also discussed that due to the benefits of FDM, it can both complement an existing process or replace it altogether. We've looked at how NOVATECH transitioned to FDM production of end-use parts, and that the benefits of FDM can be leveraged by literally any company of any size and in virtually any industry. It can transform the way that they produce plastic end-use parts. Thanks for taking the time to explore application of end-use parts with me today. I'm going to send it back to Kim for the Q&A.
Thank you. In a minute, we'll take any questions that have come in from the attendees. If you have a question, please be sure to submit it through the Q&A or chat panel to the right. After the event today, you will have access to download a copy of these slides and the webinar recording at stratasys.com/webinar-end-use-parts. Also at this URL will be links to download some additional documentation, customer story around this application. And Stratasys is here to support you in many different ways. You can contact your local reseller to request a benchmark be made to really get the idea how the end-use parts may work in your situation. There is also an online form where you can submit a more technical question and ask an engineer. Okay, now on to the Q&A. Looks like a few questions have come through, so we'll try and get through most of these before our time runs out here today. Here is one from Carlos, who asks, can I use existing CAD drawings of my parts, or do I need to redesign them or use special files? And how do I optimize my design for FDM?
So kind of a two-part answer to a two-part question. The short answer is yes, you can use existing 3D CAD files. The better answer is that it's better to go ahead and incorporate design for FDM principles. So again, you can remove unneeded features that are in there only for use when you're doing, say, an injection molding process. You can remove those and design purely for performance. You can take advantage of design for FDM principles like sparse fill and self-supporting angles in order to reduce your build time. I think you'll be much happier with the results.
Great, and I think part of the question was also, basically what you need is to use your current CAD software, anything that's 3D CAD, and then convert that file, export it to an STL file, and then that STL file then you can import into your Stratasys software that comes with the system in order to process the file and get it ready to print.
That's a good point.
I think that was probably one of the other parts there. Okay, so let's take a look at another question here. Kelly would like to know, she says, my parts will see operating temperatures in excess of 150 centigrade, and are FDM materials and parts still an option for me?
Absolutely. For end-use parts, taking into consideration operating temperature and operating conditions is a must. With the 150 degrees C that you kind of put out there, I think the options would be our engineering polymers, our Ultim 9085, or our PPSF. For some of the other people out there that are wondering about their specific conditions, Stratasys has a wide variety of thermoplastics, and all of those material specs are available on stratasys.com. So I encourage you to be familiar with those and really understand your application and then cross-check that with those specifications.
Perfect, yep. Here is another question. Does it require a separate machine if I need to manufacture parts out of different materials that have different material properties?
I'm glad you asked that question because it's actually a point that I kind of neglected to make during my presentation. It's, again, one of the benefits of FDM is that the material comes prepackaged in either canisters or cartridges. So the short answer is you only need one machine, and you can go ahead and swap out the canister or cartridge to switch to a different material. In fact, the Fortis 900 MC has a great feature in it, a wizard that takes you through that entire process. So you can switch from, say, ABS M30 to nylon and go ahead and print your part in either material.
Great. Okay. Looks like we have time for about one more question, so we'll take that one now. Dan wants to know, he says, I currently use injection molding to manufacture my parts. Will it be evident to my customer that I've switched to using FDM?
So kind of another two-part answer here for you. On the functionality side, they won't notice any difference. The part will function exactly the same. Aesthetically, they'll notice a slightly different surface finish. In most cases, that's not an issue. Some people even prefer the surface finish of an FDM part. For other people, if they really want to try and make that surface finish match that of their injection molded part, there are secondary processes that they can put into use, and that includes sanding or vapor smoothing or matte finishing. And usually that can kind of bring that surface finish back into line with your requirements.
Great. Well, thank you, Jeremy, for the answers and your presentation. It looks like our time is up. If we didn't get to your question on the call, we will be sure to follow up with you via email. Thanks again to all of you for your attention during the presentation, and now I will turn it over to our operator who will close out the event. Bye-bye.